29th. That must have been an accident, but I'll fix that today. Arib, you have a question?
Yes, ma'am. I want to know if there's a possibility that you can record the lecture.
Is the TA in here today?
Because I have to be in the final project preparation and I cannot take the class right now.
Okay. Colburn is recording it, and he's going to put it on Google Drive. Is that okay?
That would be great.
Okay.
Thanks,
Colburn. You're welcome. So all previous homework due for half credit is due. No. Okay. The adaptives were due on Friday. All the normal homework is due on the 29th. So, yeah. So the normal homework for exam 5. So exam 5 homework due on the 29th. Adaptives were due on Friday for half credit for a late grade. That was a good question, though. All right. So let's say we have this reaction here. We have zinc and iron. So even if my adaptive grades stopped increasing, even if I got one right. Yeah. So let's say you got a whole bunch of them right and you ended up with like a 5. I would change that. So it's going to take me a long time to get the grades changed, but I will get them changed. So that's what I'll be working on over the next couple of weeks. This week and finals week is getting everything just so once I get everything set, then I'll email everybody so you can check it. But it probably won't be this week. I'll be working on it this week, but it probably won't be finished this week just because there's so many grades to go through. Because for each, well, I don't know. Well, yeah. There are a bunch of adaptives, and for each adaptive, I have like between 200 and 300 students to go through for every adaptive. There've got to be about 10. That's a lot, but anyway, but I'll get it done. And I'll let you know when that happens. Let's see, the bonus for each test, if you go to assignments, there's due dates on the assignments page. And also if you go to the announcements on D2L, that'll show you as well. Yeah, exam 5 is the only one that's left. All the other ones have passed. Yeah. So the adaptives for exam 5, you can still do. Those are everything associated with exam 5 is still due on the 29th. Chad, you have got a question.
Yeah, it said adaptive 8B was due on the 23rd for me, but the rest of them are due the 29th.
Yeah, I've got to go in there and fix a couple of those. I think I just missed one or two, but I'm going to fix that today. Somebody had mentioned that a couple minutes ago, and I'm going to get that fixed.
Okay, thank you.
You're welcome. And Joshua, you have a question.
Yes, I've been emailing you in regards to the extensions for my assignments and stuff, and I was wondering when you were going to be able to get back to me on that.
Today.
Okay, thank you.
You're welcome. Amelia, because I only see bonus for exam 1. I've done all. Oh yeah. Okay, so I have to go in there and do that as well, Amelia. I haven't done that yet. So as long as you did the bonus, you can just add 5 points to your grade. But they'll actually be added this week. So the bonuses are not a big deal. Those I can get done relatively quickly. So it's kind of a balancing act between the grading and the emails. So when I start to catch up on grading, then the emails start to get behind, and then I start to catch up on the emails and the grading gets behind. So you'll notice when I start to grade stuff, the emails will fall back, and then when I start to catch up on emails, then the grades will go back. So past week, I think I was doing grading for the other chem class, because believe it or not, as sad as it is, you guys have more stuff graded than they do. And then for an SCM class also. And that, the Vesper model, I'm actually really looking forward to grading the Vesper models. So that should be done this week too. So I would have gotten more done on Friday, but I had that COVID shot on Thursday. I just did not feel all that great on Friday. But I'm back and feeling normal now, so that's good. Yeah, I didn't feel as bad as my daughter did. My daughter felt horrible. She had a fever for like 2 days, but I didn't have a fever at all. I just kind of felt washed out. Joshua, do you have another question?
No, I'm sorry.
Oh, that's okay. I'm sorry you felt so bad, Summer. No, that's a good question. All right, so let's do an example here. So we've got zinc. We're going to add to it iron 3+. I'm just doing the net ionic equation for this. Well, you know what? Let's not. Let me make it less complicated and confusing. I'll do iron chloride. And on the other side, I'm going to have iron metal. And zinc chloride. I think zinc is 2+, is that right? Yeah, zinc is 2+. All right. So that would be zinc, oh, that's too low. Cl2. All right. And then we can kind of balance these, but I just wanted to show you this as kind of a starting place for the net ionic equation. When you get down to the net ionic equation, what you're going to see in the end is, oh, that's a good question. And actually, we're going to get to the activity series today, and that's going to give you the answer there for that. In this case, if there's a reaction, what's going to happen is the zinc will replace the iron. All right, so I just wanted to show you kind of where you could get this net ionic equation from. Iron 3+. Iron solid plus zinc 2+. Okay, so here's a net ionic equation that we're going to work with. I'm going to show you how to figure out how many electrons are being transferred. All right, so the first thing to do is just separate them out. So I'm going to put all the zinc in one reaction and all the iron in the other one. So you can kind of see what I'm doing here. So zinc solid goes to zinc 2+, and I should have had an aqueous symbol on that last one. What happened to the chlorine? The chlorine would have been a spectator ion and would have been crossed out. That's a good question. I just didn't go to the trouble to show you all the steps. I just didn't want you to be like, I didn't want you to think that you can add iron 3+ without it being attached to something. So just kind of wanted to show you where that came from. All right, and the other one is iron 3+. Is it still a spectator if the charge changes? It is not a spectator if the charge changes. That is a good question because it's something different. Okay. So what we see on the left with the zinc one is we have a completed zinc with all the electrons and all the protons. Oh, okay. So spectator ion is something that when you write out the entire ionic equation, the spectator ions are going to be the ones that cancel out. So if we have time, I'll do an example. If we don't, if you stop by during office hours, I'll do an example then. All right, so when you're trying to decide whether or not they're oxidation or reduction, just remember losing electrons is oxidizing, and so zinc lost electrons, so that was the oxidation. And then iron gained electrons, so that was reduction. So how many electrons did zinc lose? If it went, yeah, 2, correct. Because it went from neutral to 2 plus. So we're going to put the electrons on the right-hand side. All right. And the reason we do this is because if you add zinc 2 plus and the 2 electrons, what you get is a neutral zinc, which is on the other side. If I did it the wrong way and I put the electrons with the neutral zinc, I wouldn't get zinc 2 plus. I would actually get zinc 2 minus. So, for example, if I did it, I'm going to put this one in red because it's wrong. Right here. If I did this instead, and you'll see it in just a second. I don't think you can see it when I'm typing. Right. So if I put the electrons on the left instead of on the right, what I'm going to get when I add zinc and the 2 electrons would be zinc 2 minus, not zinc 2 plus. So I can't do this, right? This wouldn't make any sense. So it only makes sense to add the electrons on the part that has the positive. Right? So how many electrons were added to the iron? 3, correct. All right, I put them a little too far over to the left, but you can kind of see them over there in purple. Correct, added to the left side, that is correct. And so if we add iron 3 plus and the 3 electrons, then we get a neutral iron. Now, we have to do what's called balancing the redox reaction, which is similar to the way we normally balance it, but we want them to all have the same number of electrons, because if one of them lost 2 and the other one gained 3, then an electron just kind of floated in out of nowhere, which doesn't happen. So we have to have the same number of electrons being lost as gained. So Hunter's right that we're going to multiply the equations. So yeah, correct. So the one on the top has 2 electrons and the one on the bottom has 3. There's not a whole number I can multiply 2 by in order to get 3. There's not something I can multiply 3 by in order to get 2. It's a whole number. So what I'm going to do is I'm going to multiply the top one by 3.
Okay, so the messes will be going
And
for
the
3
bottom
weeks.
one I'm going to multiply.
The mess is
by
going to be going for 3
2.
weeks. She had an emergency.
Let's see if I can move it over far enough. And so then I should get 6 electrons on the one on the top and the one on the bottom. And I've got a video to show you this again in a couple of minutes when we do the acid and the base balancing. All right, so then that's going to be 3 zinc solid plus not plus, makes 3 zinc 2 plus aqueous plus 6 E minus. Okay? And then the bottom one is going to be 6 E minus plus 2 Fe 3 plus aqueous and that makes 2 iron solid. All right, so we got the general gist of the main difficulty. So the harder part. Now in the end, to get the full balanced equation, what we're going to do is we're going to add them together and cancel out things that are on either side. Just like when we did the net ionic equations, and if it was the same on the left and the right, we canceled them, we're going to do the same thing here. So I can write the entire thing out so that it'd be 3 zinc solid plus 6 electrons plus 2 iron 3 plus aqueous. And then on the other side, I could do 2 iron solid plus 3 zinc 2 plus aqueous plus 6 electrons. Yes, the 6 electrons would cancel out. Or I could just say, okay, what's on the left that's also on the right of these two equations? So that is going to be the 6 electrons and 6 electrons. And then you want to check the other stuff just to see if there's anything else that can cancel. When you get into the acid and base ones, you might be able to cancel water on occasion when you get to the basic solutions, but not the acidic ones. All right. So now that we've got that, we're going to just add them together. So with the chlorine, you actually would use the chlorine, but I skipped a step. I skipped the part where you go from the molecular equation to the complete ionic equation and then cancel out spectator ions and then get to the net ionic equation. And I just went to the net ionic equation. So that's why you don't see the chlorine in another step where it just disappears. So Summer's correct. It was a spectator ion. And so that's why you don't see that there. Hang on, I'll show you 1 second. Yes, that is correct. 2 iron solid. Okay, so the final answer is the one down there in purple. So you've got to go through a couple of steps, and then when you get to the part where your electrons finally balance, you cancel out the electrons or anything that's the same on the left as it is on the right. You just cancel those out and write down what's left over. And remember to put the arrow, just one arrow goes in the middle, and everything that was on the left side of the arrows goes on the left. Everything on the right side of the arrows goes on the right. All right. Okay, so now I've got a little video for you. Oh, really? What question is it? Do you know? Is it in acidic solution? Hmm, 8.7. Okay. Well, I'm going to let you guys take... Okay, number 5 for you. All right. So I'll take a look at it. Yeah, the Smart Center actually is a great place to go for that. They have in person, and I think they still have some online as well. Okay, so let me go ahead and show you this video. Yes, that's the one I want to show you. So I'm going to share that. I think it's this one. Yep. Okay. Let's see. Is it this one, guys? Now, I think before the pandemic, it was all in person, I think, but I'm not sure. Okay, so I'm going to go ahead and play this video. This is on balancing redox reactions that happen when they're in an acid. So this would be like iron something, iron plus magnesium oxide making some other stuff. But anyway, the difference is the solution is not just water. It's in an acid solution. So it's like we combine the iron substance and the magnesium oxide substance and we put them in like maybe hydrochloric acid or something. But we're not including anything but the H plus part of the acid in this. So I will let them go ahead and explain
In
that.
this example, you'll learn how to use the half reaction method to balance an oxidation reduction reaction occurring in an acidic solution. The problem reads, balance the redox equation shown here. To balance a redox reaction, you have to follow a specific step-by-step procedure. I'll guide you through each step one at a time. The first step is to assign oxidation states to all of the atoms in the equation and identify what is being oxidized and what is being reduced. So begin with Fe2+. Since the charge is 2+, the oxidation state is +2. Then, for MnO4-, the oxygen is -2, and there's 4 of them. That's a total of -8. The ion has an overall charge of 1-, so the oxidation state of manganese must be +7. Then, on the product side, the Fe is 3+, so its oxidation state is +3. And the manganese is 2+, so its oxidation state is +2. Notice that the iron has increased in oxidation state from +2 to +3, so it has been oxidized. The manganese has decreased in oxidation state from +7 to +2, so it has been reduced. The next step is to separate the overall reaction into 2 half reactions, one for oxidation and one for reduction. So the oxidation reaction is Fe2+ goes to Fe3+. The reduction reaction is MnO4- goes to Mn2+. The third step is to balance each half reaction with respect to mass, beginning with elements other than H and O. In this case, however, the Fe half reaction is already completely balanced. For the MnO4- half reaction, the only element other than hydrogen and oxygen is manganese, which is also already balanced. So the next step is to balance oxygen by adding H2O. Since there are 4 oxygen atoms on the left, add 4 H2O on the right. Then balance hydrogen by adding H+. Since there are 8 hydrogen atoms on the right, balance by adding 8 H+ on the left. The next step is to balance each half reaction with respect to charge. You're going to do this by adding electrons to the appropriate side. For the oxidation half reaction, the charge on the left is 2+, and the charge on the right is 3+. So balance the charge by adding 1 electron to the right-hand side. That makes a charge on both sides 2+. For the reduction half reaction, I will pause here and let you try to figure out how many electrons to add to which side. Is it A, add 5 electrons to the reactant side, B, add 1 electron to the reactant side, or C, add 5 electrons to the product side?
So notice what they did here was they saw that there was MnO4-, and so they realized that there were no oxygen on the right. So what they did was they added water on the right to make sure there were enough oxygen. So since it was MnO4, they added 4 water because that would add 4 O's. But then now the H's need to be added on the left because we already have some on the right. There are 8 of them, so we just add 8 H+ on the left. Correct. If you end up with an oxygen and it's in an acid solution, then you're gonna do this. Do you guys want me to rewind it and play this part again so you can see it? Okay, yeah, because we kind of got a little distracted with the, come on, do something. Oh, I'm clicking on the wrong page. That would explain it. Okay, one sec. Okay.
In this example, you'll learn how to use the half reaction method to balance an oxidation reduction reaction occurring in an acidic solution. The problem reads, balance the redox equation shown here. To balance a redox reaction, you have to follow a specific step-by-step procedure.
Now keep in mind, if you look at the top, it says half reaction of balancing aqueous redox equations in acidic solutions. So you don't do this in just every one. You just do it in acidic solutions.
I'll guide you through each step one at a time. The first step is to assign oxidation states to all of the atoms in the equation and identify what is being oxidized and what is being reduced. So begin with Fe2+. Since the charge is 2+, the oxidation state is +2. Then for MnO4-, the oxygen is -2, and there's 4 of them. That's a total of -8. The ion has an overall charge of 1-, so the oxidation state of manganese must be +7. Then, on the product side, the Fe is 3+, so its oxidation state is +3. And the manganese is 2+, so its oxidation state is +2. Notice that the iron has increased in oxidation state from +2 to +3, so it has been oxidized. The manganese has decreased in oxidation state from +7 to +2, so it has been reduced. The next step is to separate the overall reaction into 2 half reactions, one for oxidation and one for reduction. So the oxidation reaction is Fe2+ goes to Fe3+.
So what they're doing right here is they're just separating out the iron from the magnesium part.
The reduction reaction is MnO4- goes to Mn2+. The third step is to balance each half reaction with respect to mass, beginning with elements other than H and O. In this case, however, the Fe half reaction is already completely balanced. For the MnO4- half reaction, the only element other than hydrogen and oxygen is manganese, which is also already balanced. So the next step is to balance oxygen by adding H2O. Since there are 4 oxygen atoms on the left, add 4 H2O on the right. Then balance hydrogen by adding H+. Since there are 8 hydrogen atoms on the right, balance by adding 8 H+ on the left. The next step is to balance each half reaction with respect to charge. You're going to do this by adding electrons to the appropriate side. For the oxidation half reaction, the charge on the left is 2+, and the charge on the right is 3+. So balance the charge by adding 1 electron to the right-hand side. That makes a charge on both sides 2+. For the reduction half reaction, I will pause here and let you try to figure out how many electrons to add to which side. Is it A, add 5 electrons to the reactant side, B, add 1 electron to the reactant side, or C, add 5 electrons to the product side? The correct answer is A, add 5 electrons to the reactant side.
He didn't pause very long, did he? Okay. Keep in mind at the top where they do Fe2+ goes to Fe3+, they didn't neutralize it. And the reason they didn't neutralize it is because they're just trying to make it equal, right? Just trying to make it equal. I'll do an example like this in just a second, slower, so that you can kind of see how they're doing it. So if they add 1 electron on the right and you add that to Fe3+, you would get Fe2+. Then the next thing that they're showing is that manganese oxide has oxygen, but on the right-hand side, all they had was manganese. So they had to add water so they can add some water. All right. So the 5 electrons came from the fact that manganese's oxidation state was -7 on the left and plus 7 on the left and +2 on the right. So if they add 5 electrons to the manganese, which was +7, then it becomes +2. So they're just balancing the charge of the manganese there.
You get this by summing all of the charges on the reactant side and the product side. On the reactant side, you have 8H plus, which is 8 plus, and then you have 1 MnO4 minus, which is -1. So the total charge on the reactant side is 7 plus. On the product side, the total charge is just that of manganese 2 plus, which is 2 plus. So therefore, you have a 7 plus charge on the reactants and a 2 plus charge on the products. You can make the charge equal on both sides by adding 5 electrons to the reactant side. That makes the charge on both sides of the reaction 2 plus. The next step is to make the number of electrons on both of the half reactions equal. Do this by multiplying the half reactions as necessary by small whole numbers. In this case, you have 5 electron gains in the reduction, so you need to multiply the oxidation reaction by 5 so that you have 5 electrons lost in the oxidation. Now, add the 2 half reactions together, canceling electrons and any other species that cancel. In this case, only the electrons cancel, and when you add the 2 half reactions, you get that 5Fe2 plus 8H plus MnO4 minus goes to 5Fe3 plus Mn2 plus 4H2O. The last step is to check that the equation is balanced by verifying that you have equal amounts of atoms of each of the reactants and products. Set up a table with the reactants on one side and products on the other. On the left side of the reaction, you have 5 Fe atoms. On the right side, that is the product side, you also have 5 Fe, so that balances. On the left side, you have 8H. On the product side, you have 4 H2Os, which is also 8H. Hydrogen balances. For the manganese, you have 1 on the reactant side and 1 on the product side, so Mn balances. For oxygen, you have 4 on the reactant side from the MnO4 minus, and then you have 4 on the product side from the 4 waters, so that balances. Lastly, check the charge. The total charge must also balance on each side. On the reactant side, you have 5 Fe2 plus, which is 10 plus the 8H plus, which is 18 plus, minus 1 for the MnO4 minus, so the total charge on the reactant side is 17 plus. On the product side, you have 5 Fe3 plus, which is 15 plus Mn2 plus, which is 2 plus, so the total is also 17 plus. So you can see that the charge is the same on both sides. The equation is balanced.
All right, so let me do an example, a little slower than he did. Oh, wait, I think I just saw a comment. How would you balance the charge if it was not balanced? If it wasn't balanced, you just go back and recheck how you added your electrons and make sure you did that part. Kind of do the SmartWorks example. Yeah, I can do that one. Also, if you want to see some more examples of these, go and take a look at the alternate lectures. The one on redox has all this stuff in it, and it has me working all these problems. So there's me working extra examples on there. Let me see if I can find the balance the equation first and then balance the electrons. You could. Let's see. All right, so this is the one you guys want me to work, right? Okay. All right, let's see. If a nail is made of elemental iron, and what they mean by elemental iron is just iron solid. All right. And it's placed in an aqueous solution of soluble palladium-2. All right. And right, the nail gradually disappears as the iron enters the solution as iron 3, and the palladium solid forms. Okay. Correct. It's not, this one is not redox in an acidic solution. And I'll show you how you can tell that you don't have to add water or anything weird to it. Give me 1 second. What was it? Was this iron 3 plus, it said? I think it was. Okay. Plus PE solid. Not PE. Okay. So I'm going to separate it out so that I have the iron in one and the palladium in the other. And I put F3 plus. I didn't mean that. I meant Fe3 plus. Okay, so that's the first one. And the second one is this. All right. Yes, Chad, you are correct. So I'm just going to mark through that and put it right above it. Okay. All right. So now what we're going to do is we're going to try to see how many electrons do we add on both sides. So if I look on the left, looking at the iron one is neutral, meaning there are exactly as many electrons as protons. If I look at the right, I have iron 3 plus, which means that I'm missing 3 electrons. 3 electrons have been peeled off. So if I add them back, then if I add the 3 plus and the 3 electrons, that becomes a neutral iron. Now on the left of the palladium 2 plus is missing 2 electrons in order for it to equal 0, which is the charge on the right-hand side. Right? Correct. Now, keep in mind that the only reason that since it's 3 plus, I'm adding 3 electrons is because the iron on the left is neutral. If I had something different like Fe plus and then Fe3 plus, so keeping in mind that this is the charge and not just a regular plus sign. Okay, so this would be iron 1 plus on the left and 3 plus on the right. So I would only add 2 electrons here. And the reason I'd only add 2 electrons there is because when you do 3 plus and 2 electrons, then you get Fe plus on the left, which matches the Fe plus. Fe plus on the left and the right would then match. The electrons are negative, that is correct. Okay. Now, if I'm looking at these, I need to have the same number of electrons because I can't say that iron lost 3, palladium gained 2, and then 1 just left. So they have to equal. So what do I multiply the iron equation by? By 2, correct. Right? What do I multiply palladium by? Correct. All right. So when I do that, then I'm going to get, for the iron part, 2 Fe solid opposed to 2 Fe3 plus 6 electrons. And then on the bottom, I'm going to get 2, no, not 2, 6 electrons plus PD, 2 PD, 2 plus, making 2, why am I doing 2s on these? It's supposed to be 3. Sorry about that, guys. 3 PD, 2 plus. Making 3 PD solid. Okay, that's better. So now if I look at it, I have 6 electrons on the right and 6 electrons on the left, so they match. I have 2 iron on the left and 2 iron on the right, that matches. 3 palladium and 3 palladium, so that matches. And I should have had an aqueous symbol for this guy here, which I forgot. All right, so I'm going to take and I'm going to add these together, first by crossing out the things that are on the left and on the right that match. Okay. Then I'm going to write down what's left. 2 Fe solid plus 3 palladium, 2 plus, aqueous, makes 2 Fe 3 plus, aqueous, plus 3 PD solid. Okay? And if we look at the whole thing, we'll see that there are 2 iron on the left, 2 on the right, 3 palladium on the left, and 3 palladium on the right. If I was to balance this at the beginning and just leave it without worrying about the electrons, it wouldn't be quite right. Yes, you can, Hunter. So it wouldn't be completely right because we would still end up with what we had at the top, which was just Fe solid plus PD 2 plus makes Fe 3 plus PD solid, right? And you have to have the 2s and the 3s there so that the charges are correct. Because if you don't, the charges are incorrect. If I look at the left here, I have 3 PD 2 plus, which is a total of 6 plus. And on the right-hand side, I have 2 iron 3 plus, which is a total of 6 plus. Because I have a 3 plus and a 3 plus on the right, and on the left I have a 2 plus and a 2 plus and a 2 plus. So all they're adding in here now is they're not only making sure you have the same mass on the left and the right, same number of atoms on the left and the right, but you have to have the same charges on the left and the right as well, as a whole. So on the left, I do have palladium 2 plus, but since I have 3 of them, that's a total of 6 plus. And on the right, it's a total of 6 plus because I have 2 3 pluses. Does that part make sense? Yeah, we're going to go over that on Wednesday and try reviewing on Wednesday. If we run out of time, I can push the exam to Monday, and we can review on Friday. It depends on how much time we have. So keep in mind that we may be pushing the exam to Monday. We will see on that. Good. Very good. All right. So I've only got 3 minutes left, so I can't finish what I wanted to finish. So we're going to finish that on Wednesday, which was to show you how to balance it in a basic solution, which is pretty similar to the acidic solution. And I also want to give you some examples of balancing it with, I want to do some examples balancing it with acidic solutions. However, if in the meantime you want to see some examples, if you watch the additional lectures, what do I call those? Do I call them additional lectures, extra lectures? I don't remember. They're under the Exam 5 materials, under study resources. They're alternate, thank you. They're the alternate lectures. And the alternate notes go with the alternate lectures. So they pair together. Not sure how many questions yet because I haven't written it. Yes, I can do that. as well on Wednesday. I will be putting up tutorials for the exam. Okay, we can get that sorted out. Hunter, and I think I see somebody sent me another one. Stephanie, you were asking me a question. Okay. Oh, I know what you're talking about. You're talking about when they were assigning oxidation numbers. Yes, they were using the order of priority. That is correct. They did. Yeah. I don't know why, but I was like, I know what she's talking about, but it's just like it just would not come to my mind. But yes, you have to use the order of priority and assigning oxidation numbers. That's why when MnO4, they assigned the oxygen first, because the manganese is not in group 1 and it's not in group 2. It's a transition metal. That's why they did the oxygen first. All right. So class is over. You guys have a good afternoon. Study, but remember to eat and rest as well. And Hunter, you have a question for me before I head off to my next class.